Okay, so thank you everybody for your presence. Thank you, Nick, for accepting to present the first seminar of VIG3 of the Cost Action RQI. Nick did his master's in physics and philosophy at Bristol. He is PhD at Oxford, supervised by John Barrett. And right now he's doing his postdoc at Perimeter Institute. He had experience with quantum causal models, relationalism, including Wigner-Franz scenarios, and also in the end of his PhD, he combined insights from these areas to develop an interpretation of quantum theory based on causal structure. And right now, he's interested in the intersection of causal structure and quantum reference frame, deriving theory from causal structure in classical mechanics. And today, he is going to give a talk about I lost your title. I will let you to present and tell your title. Thank you very much again.
Great. So I'll share my screen then for the slides. Oh, I need to request you to share my screen.
I allowed you a red. I think you can try again.
Okay. Oh, hang on.
Take your time.
Sorry, I'm just having to give Zoom permission to. There we go. Can you see my screen now?
Yes, we see the slide, but not the full screen. We also see the slides on the corner, you know. Maybe you should put it full screen.
Can you see now?
Okay, now it's perfect.
Fantastic. Okay, very good. Thank you very much. Okay, so today I'm going to be talking about the role of causation in fundamental physics. Now, this is a title that might immediately come as a surprise to some, because it has been argued a number of times that causation actually plays no role in fundamental physics whatsoever. So very famously, over 100 years ago now, Bertrand Russell argued that causation plays no role in fundamental physics. But also more recently, there's a paper by Emily Adlam where she argues that even if the notion of causal order plays some role, the notion of causal influence itself doesn't play any role in fundamental physics. But I disagree with those claims, and I disagree about as strongly as you possibly could. Not only do I think that causation plays a role in fundamental physics, I literally cannot think of a more important concept. I think that causation is at the heart of how we need to make sense of how we need to solve the measurement problem of quantum theory. And I also think that there are pretty good reasons to think that it might help us to tackle the problem of quantum gravity as well. So those are some of the things that we're going to talk about today. Now, this is a talk that comes in 3 parts. I'm going to start by talking about a notion of causal influence as non-commutativity. And then once we've developed this concept of causation, I'm going to use that to develop this idea that I call causal relationalism. This is kind of an approach to physics. And then in part 3, we're going to take causal relationalism and we're going to turn it into a theory, an interpretation of quantum mechanics that I call causal relational quantum theory. So again, part 1, developing the concept of causation. Part 2, developing causal relationalism. And then in part 3, actually turning it into a theory. So part 1 is about this idea of causation as non-commutativity. Now, the way that I'm going to approach this is I'm going to start by just throwing a mathematical definition at you. And then gradually we're going to begin to unpick exactly what that mathematical definition means physically. So we're given a unitary channel and a couple of Hermitian operators. And I want to define a causal influence from A to B through U in terms of this non-commutativity in the Heisenberg picture. So in that expression on the bottom right, what I'm doing is I'm taking the Hermitian operator B, and I'm initially thinking of B as something that acts on the output space of the unitary channel U. But then I am rolling back B through the unitary channel so that now it acts on the same Hilbert space that A acts on. And now I can compare these operators and ask whether they commute with each other. And if they don't commute, I'm going to say that there is a causal influence between them. So there's a mathematical definition. Now, what does this mathematical definition mean? Well, one operational meaning of causal influence is this. Suppose that Alice implements the Hamiltonian A, and then the unitary channel U is applied, and then Bob measures B. Then according to our definition, A influences B through U if and only if Alice can signal to Bob in this scenario. So we've got this idea that a causal influence involves the Hamiltonian A kind of changing the observable B, but changing it via this unitary channel. Good. Now let's see another logically equivalent way of defining causal influence. A is a Hermitian operator, so it's got this spectrum. I can write it like this. And then I'm going to define an A interaction as any unitary transformation of this form. So what's going on over here is that you have this coherent control of unitary transformations. The basis of control is defined by the projectors onto A's spectrum. And then the coherent control unitaries themselves, the VIs, I'm not really assuming anything in particular about them other than that they are distinct unitary transformations. So I'm assuming that VI and VJ are not equal to each other up to a global phase. So again, an A interaction is this coherent control of distinct unitary transformations. Now, with this notion of an A interaction, we're going to be able to see another way of defining causal influence. So let's consider this circuit where I've got an A interaction, then the unitary channel, then a B interaction. As things currently stand in this circuit, the A interaction acts on a different Hilbert space to the B interaction, right? A at the input space, B on the output space of U. But we can change that by rolling back the B interaction through the unitary channel. And then once we do that, we can write down this theorem. It turns out that A influences B through the unitary channel U in the sense that we've already defined if and only if the A interaction and the rolled back version of the B interaction do not commute. So I'm not going to go through the proof of this result explicitly, but it is helpful, I guess, just to give you a little sense of the intuition behind the proof. So this rolled back B interaction, you can think about this as a kind of unitary model of a measurement. And this is just following the tradition that goes back to von Neumann of regarding measurements as coherent control unitary processes. And this might be slightly less obvious, but you can also view the A interaction as a kind of implementation of the Hamiltonian A. There's this kind of duality between implementations and measurements. And if you remember what we saw a couple of slides ago, the causal influence is equivalent to the Hamiltonian A changing the observable B through the unitary channel U, then you can probably start to see how you might be able to prove this result, that causal influence is also equivalent to the non-commutativity of these interactions. Good. So that brings us to the end of part one already. Causal influence is the non-commutativity of operators in the Heisenberg picture, but it's also the non-commutativity of interactions. When I talk about causation as non-commutativity, that actually has a double meaning. right? Operators and interactions. And so all in all, we've got this. We've got these two different but logically equivalent ways of defining causal influence. Very good. Okay, so part two is about something that I call causal relationalism. Now, before we can get straight on to saying exactly what causal relationalism is, we need to develop a couple of preliminary concepts. So for the next several slides, I want us to consider this situation where we've got a unitary channel U, just like we did before. Only this time, the input space of U is factored into two subsystems, HA and HB. And I'm saying that Alice has access only to HA and not HB. Similarly, the outputs are factorized and Dexter only has access to HD and not HC. Now, I want to introduce this notion of an operator on Alice's system being accessible to Dexter. So what does it mean to say that Dexter can access one of Alice's operators? Well, here's the idea roughly. Suppose that any change that Alice makes to the observable A can be detected by Dexter. Then we say that A is accessible to Dexter. So how do we actually formalize this idea of accessibility? Well, it's helpful to introduce this shorthand. We've already seen how you define causal influence between individual Hermitian operators. Now I'm going to define what it means for the operator A to influence the whole Hilbert space, HD, through U. And the definition is simple. We're just going to say that A influences HD if and only if it influences at least one local operator on HD. And with that shorthand, we can now formalize this idea of accessibility. A is accessible to HD if for any Hamiltonian alpha on A, if A and alpha do not commute, then alpha influences HD. Okay. So how is it that definition one is formalizing this idea of accessibility? Well, the idea is that this Hamiltonian alpha represents a way that Alice can change the observable. And then alpha influencing D, or alpha influencing HD, is the requirement that Dexter notices that change. So we're formalizing that idea that the change represented by alpha in the observable is noticed by Dexter. Good. So we've now got this formal definition of accessibility in terms of causal structure. Now put that to one side for a moment, and I want to define another concept. This concept is going to be called stability. What does it mean for an operator on Alice's system to be stable relative to Dexter? Well, suppose that Dexter cannot tell whether or not Alice measures A. Then A is stable relative to Dexter. So again, we ask, how do we actually formalize this idea? Well, remember from part one that causation is non-commutativity. It's the non-commutativity of operators, but it's also the non-commutativity of interactions. And we can show that A does not influence HD if and only if this diagrammatic equation holds. And we can think of this diagrammatic equation if you bear in mind that the A interaction can be thought of as a kind of unitary model of a measurement, then we can sort of think of this diagrammatic equation as telling us that Dexter doesn't notice when Alice measures the A observable. And that motivates the definition of stability. So A is stable relative to HD if A does not influence HD through U. Good. So let's summarize what we've got so far in part two. We've got these two concepts of accessibility and stability. We got the intuitions for them. So accessibility is about Dexter being able to access that observable, noticing any change that's made to that observable. Stability is about Dexter not noticing when Alice measures the observable. And for both of them, we've got these formal definitions in terms of causal structure. This allows us to define the notion of stable accessibility. So we're going to say that an operator is stably accessible simply if it's both stable and accessible. And the intuition behind stable accessibility is that, well, if I'm Dexter and A is stably accessible to me, that means that I know about A, right? I can access A, but it appears to me that it doesn't make any difference to the system when Alice measures A, right? So although we're used to thinking in quantum theory that measurements always lead to disturbing the system, stable accessibility is a kind of causal structure where it kind of appears, from my perspective, as if the usual rules don't apply and that certain observables are kind of noticeable, but again, you can measure them without disturbance. Good. So we have accessibility, stability, and stable accessibility. But the eagle-eyed amongst you will notice that there is this unfilled column, right? This operator algebra column in our table. And now in the next bit, we're going to see how these different concepts all correspond to some interesting operator algebraic structures. And that's going to help us to define this idea of causal relationalism. All right, so let's define some operator algebras. A is just the algebra of operators that act locally on A. D is the algebra of operators that act locally on D. And A stab D is the set of all of the local operators on A that commute in the Heisenberg picture with all of the local operators on D, right? So in that expression for A stab D rather, I'm taking the algebra D, I'm rolling it back through the unitary transformation, and then I'm taking the prime, right? And the prime means the commutant of this algebra. So it's the set of all of the operators that commute with the prime thing. And that thing, that commutant is an algebra in its own right, and I'm taking its intersection with A. So again, it's all of the operators that act locally on A that have this property, that they commute with the D operators in the Heisenberg picture. Now remember our definition of stability. A is stable relative to HD if it doesn't influence HD. And remembering that causal influence is non-commutativity of operators in the Heisenberg picture, it follows that A is stable if and only if A lives in the operator algebra A stab D. So what have we found? Well, we found that if we ask for what is the set of all of the operators on A, on Alice's system, that are stable relative to Dexter, then that set of stable operators is not just any old set of operators. It always has to form a particular structure, namely it forms an operator algebra. Now, in addition to those three algebras, let's define another one that I'm going to suggestively call A act D. And A act D is the commutant of A stab D within A. So it's the set of all of the local operators on HA that have the property that they commute with all of the operators on A stab D. Remember our definition for accessibility. If we take the contrapositive of that definition, then we can say that A is accessible if it's true that if alpha is in A stab D, then alpha and A commute with each other. And that's just another way of saying that A is accessible if and only if A lives in this algebra we've just defined, A act D. So what have we learned here? Well, we've learned that just like the stable operators, the set of all of the accessible operators on A is not just any old set. They form an operator algebra. So we've learned that, but that's not all we've learned. We've also learned that this algebra of accessible operators has a very specific relationship to the algebra of stable operators. Namely, each one is the commutant of the other, right? There's this duality between stability and accessibility that might not have been obvious from our initial definition of these concepts, and yet it's there. So to summarize the situation here, we've discovered that the accessible operators form an algebra, the stable operators form an algebra, but also that an operator is accessible if and only if it commutes with every stable operator. And an operator is stable if and only if it commutes with every accessible operator. Again, there's this duality between stability and accessibility. One of the consequences of that duality is that if we ask about the stably accessible operators, so remember, those are the operators that are both stable and accessible, all of the different stably accessible operators have to commute with each other. And they form a commutative subalgebra, namely just the intersection of A stab D and A ac D. Now, if you're somebody who is familiar with a bit of operator algebra theory, then you'll immediately be able to spot that this situation allows us to use a known result about operator algebras to say a bit more about their structure. So here's what we can say. There exists a decomposition of the Hilbert space of Alice's system into this direct sum of tensor products. We've got these factors HLI, which I'm going to call the left factors, and HRI, which I'm going to call the right factors. And then our three algebras have this pretty nice form. So an operator is accessible if and only if it acts trivially on all the right factors. An operator is stable if and only if it acts trivially on all the left factors. And an operator is stably accessible if and only if it's both stable and accessible. And so that means that an operator is stably accessible if and only if it acts trivially on all the left factors and the right factors, meaning it's got this trivial block diagonal form. In each block, it's just a scalar multiple of the identity. Very good. So now we can fill in that missing column in the table. We have these notions of stability, accessibility, and stable accessibility, causal definitions, but now we can also see that all of these concepts correspond to these mathematical structures, to these operator algebras. And now that we've got this sort of framework of concepts, but also framework of related mathematical structures, we're finally going to be able to make sense of the idea that gives this part of the talk its name. We're finally going to be able to make sense of causal relationalism. So first, let me just try to say what causal relationalism is at the abstract level without any mathematics yet. You can kind of break down causal relationalism into two ideas. Causalism is the idea that kinematical notions, including states and events, emerge from causal relations. If you're a causalist, you think that causal structure is fundamental, and you don't want to take your kinematical notions for granted. You want to kind of derive them or see them emerge out of a more basic causal structure. Relationalism says that kinematical notions are defined only relative to systems. So, for example, a relationalist might want to say that you can't talk about the state of a particle per se. Maybe you can only talk about the state of a particle relative to another particle. So an example of a relationalist way of thinking about quantum mechanics would be Carlo Rovelli's relational quantum mechanics. So we got this idea of causalism, we got this idea of relationalism, and you might be able to spot that there's an obvious connection between these ideas. Causalism serves as a possible explanation of relationalism. Why is that? It's because if kinematical notions emerge from causal relations, then it comes as no surprise that they should end up being relational themselves, right? They're going to inherit the kind of relationalism of the causal structure that they emerge from. That's the idea. And indeed, this is essentially the idea behind causal relationalism. Causal relationalism says that kinematical notions are defined only relative to systems because they emerge from causal relations. So causalism is true, relationalism is true, and relationalism is true because causalism is true. Okay. So how do we actually make sense of this idea? What does it mean to approach quantum theory in a causally relational way? Well, now that we have developed an understanding of causation as non-commutativity in part one, and in this part of the talk, we've developed an understanding of stability and accessibility, we're going to be able to make sense of this idea. So here's a very central idea of this talk. I propose that stable accessibility is the causal mechanism through which kinematical notions emerge. Stable accessibility is the causal mechanism through which kinematical notions emerge. How does that work? Well, remember, the stably accessible algebra is this nice commutative algebra that has this sort of trivial block diagonal form. And this is a unique decomposition, by the way, or at least the division into orthogonal subspaces of the Hilbert space is unique. And what this does is it allows us to define the notion of an event. So I want to propose that this variable I in the decomposition of the Hilbert space takes a value relative to HD. And I'm going to call this taking of a value an event. So for example, if I say to you, I equals 3 relative to HD, that sentence describes an event. That sentence describes an event. We can think about this event as being represented by a projector that I'm going to call A up 3. The reason for that notation will become clear later. And it's a projector onto that subspace from the decomposition that we saw a few slides ago. So again, an event you should think of as a kind of selection of a unique subspace in this decomposition of the Hilbert space that we get from stable accessibility. And this event determines the value of all of the observables that are stably accessible to HD. So if I equals 3, the idea is that we can infer that the eigenvalue of A is A3, right? Where A3 I'm taking from that expression that you see at the top of the screen for the stable operators, or sorry, the stably accessible operators. Okay, so this proposal is causalist, because I'm saying that events emerge from causal structure, right? That decomposition of the Hilbert space, it comes from stable accessibility, which is a causal notion. It's relationalist. Remember, I said that I equals 3 relative to HD. The idea here is that events only happen relative to systems. But it's also causally relationalist, because the relativity of events follows from the relativity of causation, and in particular the relativity of stable accessibility. So there's no absolute fact about whether an operator is stably accessible. It is going to be stably accessible relative to some systems, but not stably accessible relative to other systems. And it's that relativity of stable accessibility that creates the relativity of events. Good. So now let's develop this proposal further. So far, I've developed causal relationalism in a very, very specific context, right? Where we've got this particular unitary channel with 2 inputs and 2 outputs. And that's all right for now, but ultimately physics can involve scenarios that are a lot more complicated than that. So I want some means of generalizing all of these ideas. And we'll take this one step at a time. So let's revisit this circuit that we saw earlier in part 1, where we have the A interaction, then the unitary channel U, and then the B interaction. And for convenience, I've now labeled some of the Hilbert spaces. Now let me ask this question. What operators on HA are stably accessible relative to the combination of HB and HY? This is a non-trivial question because HB and HY appear at different heights in our circuit. And by the way, I should have mentioned earlier, time is flowing from the bottom to the top of the page whenever I write down a circuit. So HB and HY live at different times, and so it doesn't really make sense to define their combination using the tensor product, right? So we have to ask, what even does the combination of HB and HY mean? How do we make sense of that idea? And it's easy to when we work in terms of operator algebras. So let me denote by B tilde and Y tilde algebras that are rolled back, right, through all the unitary channels in the circuit so that they now act on the input Hilbert space of the entire circuit. So we're thinking of these operator algebras in the Heisenberg picture, essentially. We can define the combination of HB and HY with the combination of their operator algebras. And the combination of their operator algebras, the combination of their operator algebras is just the algebras that the two algebras generate, right? So it's the smallest algebra that contains both of them. And then we can define these operator algebras for stability and accessibility and stable accessibility, right? So I'm just writing down expressions that are analogous to the expressions that we've already seen and defining stable accessibility that way. And that's how we answer this question, right? That's how we define stable accessibility relative to a combination of systems. It just involves taking the combination of their operator algebras. Good. So now we've got this notion of stable accessibility relative to a combination of systems in a circuit. And we're going to develop this idea even further. So, oh, there seems to be this squiggle on my screen. I wonder if I can get rid of that.
You should have on the left bottom corner some edit button, and you click on that. You can then erase annotations.
Oh, yeah, it's just I can't see my cursor, which is a bit weird. I wonder if I just do this, will it go away? Oh no, now I've lost. Here, I've lost all control.
Maybe Natalia, since you're host, I think that you can probably also erase all annotations.
Yeah, I was trying to erase, but it looks like I can only erase things that I do by myself.
That's usually the case, but as host,
Yeah.
okay, it might be that you're not. Okay.
Yeah, I'm not being able. There is a little pen, Nick, on the just below.
Yeah, so the problem I've got is I kind of can't see my own cursor. Oh, wait, hang
Okay, you got it. I don't know
on.
how.
Okay, so now technology. Yeah, it's really weird. I can't see my own cursor, so it's quite okay. There we go. Fantastic. Crisis averted. Okay, right. So now I want to define this idea of a bubble. So, what is a bubble? A bubble is any subset of a set of unitarily interacting subsystems. So when you see a unitary circuit, right, any combination of individual wires in the circuit defines a bubble. And members of a bubble, I'm going to represent using gaps in wires. So if you look at that circuit on the right, where there are 4 gaps in the wires, that tells you that we're looking at this system which has, that tells you that we're looking at this bubble which has 4 systems in it, right? Namely HX, HA, HB, and HY. Okay. Now for every member of this bubble, we're going to define two algebras of stably accessible operators. So for example, for the system HA, we're going to define A up, which is stably accessible to the future of HA within the bubble. And we're also going to define A down, which is stably accessible to the past of HA within the bubble. Now, what does this mean? Stably accessible relative to the future, stably accessible relative to the past. Well, for example, in this circuit, A up B is going to be the algebra of operators that are stably accessible relative to the combination of HB and HY. The reason for that is that if you look to the future of A, the systems within our bubble that are to the future of A, so they come higher up than A in the circuit, they are just HB and HY. So that's what tells me that in my sort of future stably accessible algebra, it needs to be stably accessible relative to the combination of HB and HY. If I'm talking about stable accessibility relative to the past of A, so this A down algebra, that would just be stable accessibility relative to HX in this example. And admittedly, we haven't explicitly talked about stable accessibility relative to the past, relative to something lower down in the diagram yet. But to see that you can make sense of that idea, you just have to note that unitary circuits are time symmetric. You can always invert them. And also the notion of causal influence here, that's also a time symmetric notion. So you can define stable accessibility relative to the past in exactly the same way that we've already defined it relative to the future. Good. So again, the idea here is that for every system in a bubble, we get these two algebras, one that's stably accessible relative to the combination of everything in the future, and the other is stably accessible relative to the combination of everything in the past. Now remember our discussion of events. An event is represented by a projector onto a subspace in one of these decompositions, and we saw how you sort of could derive those decompositions from stable accessibility. Now these projectors that are stably accessible in a bubble, when they're stably accessible to the past, they commute with each other. Right? That's not too hard to show. It really just follows from the definition of stability in particular, that these things have to commute with each other. But also all the different projectors that are stably accessible to the future, they all have to commute with each other too. So the only way that you can have a stably accessible or two stably accessible operators that do not commute with each other is if one is associated with the past and the other one is associated with the future. And this fact about commutation turns out to be very significant. So it allows us to define these projectors. So what I'm doing here is I'm taking stably accessible projectors that pertain to all the different systems, and I'm taking all the stably accessible relative to the future projectors, and I'm sort of matrix producting them, and then defining a new projector by doing that, right? So the fact that these different projectors commute with each other means that their matrix product is inevitably going to be a projector. And I'm doing that for the projectors that are stably accessible to the future, but I'm also doing that for the projectors that are stably accessible to the past. And this means that the events associated with our bubble admit a natural probability distribution. So this expression on the screen has to define a probability distribution. And we've been looking at a particular example, but actually there's nothing special about our example. There's nothing particularly special about this unitary circuit. There's nothing special about the bubble in this circuit that we've been considering. Any bubble of n systems in any unitary circuit admits a probability distribution of this form. So not only do we have this notion of events that emerge from causal structure and happen relative to a bubble, we also see that these events always admit a natural probability distribution. Now, some of you might be familiar with consistent histories. And for those of you that are, I'll note that another way of saying this result is that any bubble defines a unique, consistent set of histories where the initial state is maximally mixed. So what we see here is a way of using causal structure to extract unique, consistent sets of histories. But I'm not going to go into that anymore. And for those of you who aren't familiar with consistent histories, don't worry, we're not going to rely on consistent histories anymore. Good. So that brings us to the end of part 2. And we've come a long way, so let's summarize what part 2 has involved. Stable accessibility. So an observable is stably accessible to HD when Dexter notices when Alice changes A, but he doesn't notice when she measures A. So in this situation, to Dexter, it kind of appears as though A can be measured, but it can be measured without disturbance. That's the intuition behind stable accessibility. And we found that stable accessibility corresponds to a nice mathematical structure. The stably accessible operators form this commutative algebra. And so they're associated with this decomposition of the Hilbert space. And this gives us a notion of an event, an example of which being I equals 3 relative to HD. And this idea of a relative event generalizes. So rather than just talking about an event that's relative to a system, we can actually talk about an event that happens relative to an entire bubble. For a bubble of n unitarily interacting systems, we can define stably accessible commutative algebras, or 2n stably accessible commutative algebras. And we can postulate that 2n events happen relative to this bubble with a probability given by that rule. Very good. Maybe I'll pause here for a minute or two in case anybody has any questions they want to ask at this point before we move on to part 3.
Is there someone? Please go ahead.
Now, in all your examples, your time was basically a fully ordered path.
Yeah.
If now causal is a partially ordered set, all this reasoning will survive in case you have like cones and things like that?
Can you repeat that very last part of your question again?
Okay, causality is a partially ordered set.
Yeah.
So all your scheme, now I couldn't follow completely as you were talking, will survive in case your causality is a partially ordered set. So you will have things which commute, non-commute, causal diamonds, and all the structure of local quantum field theory or realistic models of this kind.
Yeah. If I understand you correctly, the answer is yes, and more generally, in fact, so in this talk, I've been focusing on the case of circuits with definite causal order. That's only for simplicity, really, and in fact, you can consider much more exotic processes that sort of aren't even causal, don't even have a definite causal order. You can have sort of closed time-like curves, and you can actually still define stable accessibility in the same way, and the probability expression that I've written down still works.
Okay, thank you.
Cool. So any other questions at this stage about causal relationalism?
Yes, maybe from my side, if you wanted to apply what we are just seeing, what you constructed this way of getting these probabilities, trying to make contact with situations where you would usually describe of having some initial state that then is evolving. So presumably you would use some operational approach to kind of construct this initial state from earlier sort of processes analogous to this at earlier times in your circuit, so to speak, or how would that work?
That's a brilliant question. Yeah, that's a great question to ask. So summarizing, the question is, like, how does the state come into the picture, right? How do we get back to this kind of familiar idea of there being an initial state that gets evolved through time via the dynamics? That's going to be a big part of what the next part of the talk is about, so I won't try to answer that fully now, but to kind of anticipate the basic answer to the question, we have a notion of events emerging from causal structure here. The notion of a state is going to be essentially, it's a kind of tool that we use to calculate the conditional probabilities of events. So this idea of a state evolving through time, it's not really going to play a fundamental role in this approach to quantum theory, but it is going to serve as a kind of useful heuristic or calculational device.
But I guess from what you are saying, I suppose we will see it in more detail, but this conditional probabilities is maybe connected to what I was saying, that, operationally, what happened in the past or the structure you have in the past will play a role analogous to, similar to this initial state through these conditional probabilities, I guess. But I suppose we will see that in your next part.
Yeah. So let's
Thank you.
Cool. Thanks for the questions. Good.
Nick?
Oh, yeah.
I have one quick question.
Sure.
So when you talk about your event that is defined as a selection of one value for...
Yeah.
Is this a measurement? Can I understand it this way?
I would say that I guess the answer is sort of depending on your definition of a measurement. I would say it doesn't have to be a measurement, but it could be.
Okay.
Right. So if by measurement we mean something that's done by like a human being, someone in a lab coat, then I would want to say that on this approach to quantum theory, I am going to want to say that the outcome of a measurement is one of these events, or it's a collection of these events, but I don't want to say that all of these events are, outcomes of these measurements conducted by some scientist wearing a lab coat. They could be the results of an interaction between two particles interacting in some distant corner of the universe without any observer ever knowing about it.
Okay, thank you very much.
Cool, thanks. Great, okay. So now we've developed this idea of causal relationalism. And in part 3, we're going to turn this into a theory that I call causal relational quantum theory. All of the ingredients are already in place. You might feel you already have a pretty good sense of what this theory is going to involve. There are not really going to be any surprises here. But I think it is worth just kind of taking the time to explicitly say what this theory involves. So let's use causal relationalism to provide an interpretation of quantum theory. Before actually laying out that interpretation, I will say one or two things about what I mean by this word interpretation. And I think it's important to do that because it is a word that often means different things to different people. So importantly, by interpretation, I mean more than just a story that helps us to make sense of the quantum formalism. I mean more than just a story. Instead, interpretation here, it just means a more precise version of the theory. And specifically, it doesn't rely on any vague notion of measurement or observers. So this is part of what's behind my response to Natalia's question, right, about measurements. I want this to be an approach to quantum theory that doesn't presuppose any concept of measurements, which isn't to say that I don't want to be able to talk about measurements, but I don't want the idea of measurement to be a part of the kind of basic system of concepts that we're using here. So since an interpretation is just a more precise version of the theory, it should really come with its own mathematical formalism that precisely articulates its conceptual claims. In essence, all I'm saying on this slide here is I'm not thinking of things as involving, we've got a theory over here and then an interpretation over here. The interpretation is the theory, and it's just a better version of the theory that you already have. Okay, so with that in mind, here's a proposal for an interpretation. Reality is described by a unitary circuit. No state is inserted into the bottom of that circuit. There is no initial state of the universe. So this relates to that second question. We'll come to see later on how the state does sort of come back into the picture. Therefore, the circuit should not be thought of as a rule for transforming states. Instead, the circuit is really a thing in itself, right? And it's a thing out of which events emerge. Specifically, relative to a bubble of n systems, two n events happens, and each of these events is a selection of a unique Hilbert subspace from the decomposition of a stably accessible algebra. That's a bit of a mouthful, but it's just the notion of an event that we already developed in part 2. And something else we developed in part 2, the probability that a particular collection of 2n events will happen is given by this rule. So just to clarify the role of probabilities here, the causal structure determines what operators are stably accessible. And in doing so, the causal structure determines the space of all possible events, right? The causal structure determines which events might happen. But the causal structure does not determine exactly which collection of events actually will happen. Nothing predetermines that, which is why we need a probability rule, right? We can only talk about how likely it is that a particular collection of events will happen. The way that I like to interpret these probabilities is pretty standard, right? I'm not interpreting probabilities in some kind of radical Everettian-like way. The idea is that only one collection of events actually happens, and the probability is just telling you the likelihood of that, whether you think likelihood means relative frequencies or whatever you think that means. Okay. In short, causal relational quantum theory claims that reality is a unitary circuit and the relative events that emerge from it via stable accessibility following the probability rule. That's the core claim of the theory. We've already seen the formalism developed for this, but I will just repeat what it is for kind of completeness. Formally, a model in causal relational quantum theory consists of 3 things. A unitary circuit, of course. Algebras, right? So for each bubble. Oh, was that a quick? Okay, no. So for each bubble of n systems, we've got these 2n algebras. And also for each bubble, we've got this probability distribution. Now I'll note that number 1, the unitary circuit, is the only thing here that you actually get to choose when you're choosing what kind of model you want to build. Once you have chosen the unitary circuit, everything else is simply a matter of calculation. And the reason I emphasize this is that this kind of gets at the heart of what makes causal relationalism or causal relational quantum theory quite different to most physical theories. We're more used to the idea that not only do I get to choose a circuit, but I also get to choose some initial state, right? But there's no choice of initial state here. There's no choice of any kinematical notion. Remember, this is a causalist approach to physics, which means that the kinematics is emerging from the causal structure. Good. So that's enough of talking about causal relational quantum theory in the abstract. Let's see how it actually applies to a physical situation. And we're going to return to this by now very familiar unitary circuit. And we're going to think again about this bubble of 4 systems. And for concreteness, let's suppose that A and B are given by this Z Pauli operator. Then we can calculate the stably accessible algebras. And once we do those calculations, we will find that the B up algebra is the span of the computational basis operators, and the A down algebra is also the span of computational basis projectors. And these algebras are particularly interesting in this model. So we can calculate the probabilities for all of the events, all of the 8 events in this model, but then we can marginalize that, and ultimately we can do Bayesian inversion to calculate the conditional probability of B prime given A. So B prime is the event that's associated with B up, and A is the event that's associated with A down. And we find that this conditional probability is given by a very familiar expression, right? It's just this transition amplitude. And this transition amplitude expression, that's what you would find if you looked in a textbook on standard quantum theory, and you were looking for what is the probability that I'm going to get the outcome B prime, given that I prepare a system in the state A, and then I evolve it with the unitary transformation U. So going back to that second question that I answered at the end of part 2, here's where we start to see the states coming into the picture. States are not inputs to the circuit, but we see here in an example that they do serve as tools for computing conditional probabilities of the events that emerge from the circuit's causal structure. Right? So not only do we have events emerging, but we also kind of have states emerging as tools for computing these conditional probabilities. This again is the causalism at play in CRQT. So this is why I say that this model describes a prepare measure scenario and reproduces the standard quantum predictions. We now see that the A interaction behaves like a state preparation. We see that the B interaction behaves like a measurement. Now, the word measurement and the word state even doesn't play any role in the axioms of the theory. And yet, nevertheless, we see a posteriori, once we analyze models, that we see things that look like a measurement, or we see things that look like a state preparation, right? So for an analogy, classical mechanics is another theory which, like CRQT, doesn't mention measurement in its axioms. But of course, we can still model a measurement using classical mechanics, right? We can write down a model and we can say, oh, this process kind of behaves like a measurement. That's what's happening here with the B interaction. But then the disanalogy with classical mechanics is, in classical mechanics, the word state does appear in the axioms, right? So you would insert an initial state into a circuit in classical mechanics. Whereas here, we're not even doing that. The notion of state preparation is similar to the notion of measurement in CRQT. Both of them are high-level emergent notions rather than fundamental ones. Okay, but the prepare measure scenario is not so exciting, right? It's kind of a boring experiment. Let's now see something a little bit more exotic. Wigner's friend scenario. So in a Wigner's friend scenario, we have the preparation of some particle in a quantum state. And in this circuit, that's going to be represented by this A interaction. Then we have Wigner's friend performing a measurement. Then that measurement being undone by the kind of inverse of the unitary that represents the friend's measurement. And then we got Wigner's measurement at the end there. Now, by analyzing what happens in the Wigner's friend thought experiment according to CRQT, we're going to start to see how the relational aspect of the theory really comes out, because we're going to see that various different things happen relative to different bubbles. So let's begin looking at this bubble. You can see that this bubble is basically the same as the bubble that we were looking at in the prepare measure scenario. And indeed, so the bubble includes state preparation and the friend's measurement. And indeed, the stably accessible algebras and probabilities are exactly as they were in the prepare measure scenario. So in particular, we can again calculate the probability of B prime given A, and we get this expression again. So when we look in this bubble, it just looks like a normal prepare and measure experiment. Nothing particularly strange is manifested at the level of events and statistics. Now let's kind of switch to Wigner's perspective. So this is a bubble. If you look at the wires that have gaps in them on the right of the screen, this is a bubble that includes state preparation and Wigner's measurement, but it doesn't include the friend's measurement. I'm not going to go through all the details in the interest of time, But, well, essentially, it again just looks like another prepare measure experiment, but this time it's Wigner's measurement that we're considering. It's actually as if the friend's measurement has never taken place, which should come as no surprise, given that, as I mentioned earlier, the friend's measurement is kind of being undone. One thing this clarifies, by the way, is that CRQT reproduces the predictions of unitary quantum theory, right? It's not reproducing the predictions of like a objective collapse version of the theory. Okay, so now we've seen a bubble that includes state preparation in the friend's measurement. And we've seen a bubble that includes state preparation in Wigner's measurement. An interesting question to ask is what happens in a bubble that includes state preparation and the friend's measurement and Wigner's measurement, right? Whose perspective is going to win out there? So this is a bubble that includes state preparation in both measurements. And to understand what goes on here, really the crucial thing to realize is that Wigner can tell whether or not the friend has performed a measurement, right? That B interaction in the circuit really makes it different to HZ, which is the system representing Wigner. And as a result, you can show that these projectors, which in the first bubble, these projectors defined the measurement outcome of the friend, now these projectors are no longer stable. So they're not stably accessible, and they're not going to correspond to events. All right. So what is stably accessible in this new bubble? Well, if we calculate B up, right, which again, so that's the algebra of operators that are stably accessible relative to the combination of all of the systems in the future of HB. These stably accessible operators are trivial. They're scalar multiples of the identity. And that means there's only one event that can possibly happen associated with B up, which is the event that's represented by the identity operator. What does that mean? It means that the friend does not really obtain any outcome relative to this bubble. For Wigner, on the other hand, it's just like the situation in the second bubble that we looked at. It just looks like a standard prepare measure experiment, and we reproduce the predictions of standard unitary quantum theory. So, what does this illustrate about causal relational quantum theory? Well, I guess it illustrates a subtle difference between different relational approaches. Sorry, it illustrates a subtle difference between CRQT and other relational approaches like relational quantum mechanics. With something like relational quantum mechanics, people talk about it being an island universe ontology. So the idea is that reality is relative to the perspective of like one localized observer. Here it's slightly different because events are relative not to like one system, but relative to an entire bubble. So it's not just that there's one thing that happens relative to Wigner and another thing that happens relative to a friend. You can talk about what happens relative to a bubble that includes both Wigner and the friend. But at the same time, we see in this example that it turns out that in such a bubble, the friend just doesn't obtain any measurement outcome at all. Okay. So in the interest of time, I'm not going to look at any other models in details, but some other applications that I find are interesting include Bell inequality violations. So you can write down a circuit model in CRQT that violates Bell inequalities and which doesn't feature any non-local causal influences. And that's not too surprising because the notion of causation here is very different to the notion that Bell would have had in mind when he wrote down his local causality condition. Also, the PBR theorem. So the PBR theorem is a no-go theorem that shows that if you assume that you work in the ontological models framework and you make an assumption called preparation independence, then you have to believe that the quantum state is a part of reality, or more formally, you have to believe that it's ontic. CRQT can evade this no-go theorem because it's causalist. So the kind of causalist aspect of the theory means that it actually just rejects the ontological models framework. It doesn't really fit in there because the ontological models framework assumes a very non-causalist way of thinking about physics. It assumes a way of thinking about physics where the fundamental object is the state lambda, right? Whereas for us, lambda is just a thing that emerges in certain contexts. And you can write down a model of the PBR theorem in which you don't have in any meaningful sense, a kind of quantum state appearing at the point in the circuit where the theorem might appear to suggest it does. So, interesting response to the PBR theorem there. I'll compare causal relational quantum mechanics quickly with some other interpretations of quantum theory. So people often say that precise realist interpretations fall into these three main categories: collapse, pilot wave, many worlds. But CRQT, I would say, is a precise realist theory. It's a precise realist interpretation of quantum mechanics. You know, there's no measurement problem there. There's a precise formalism, but it doesn't fall into any of these three categories. And probably the biggest difference, which I've already mentioned a couple of times, is that in CRQT, there is no quantum state of the universe, whereas there is on all three of those approaches, at least the usual way that they're done. CRQT, I would say out of the three of them, it's most similar to many worlds because all the dynamics are unitary and there are no additional variables. So both many worlds and CRQT could reasonably claim that unitary quantum mechanics is complete. So what makes CRQT different to many worlds? Well, there's the point about causalism that I already mentioned. But another difference is that unlike many worlds, CRQT is a genuinely probabilistic theory. Now, looking at the last couple of bullet points, you might wonder, like, is there a contradiction here? Because we're saying that CRQT is unitary, but also probabilistic. But the unitary dynamics are deterministic. And the answer to that is that the unitary dynamics are deterministic if you think that the job of the unitary dynamics is to tell a state how to evolve, right? But if you think that the job of the unitary dynamics is to kind of give birth to these events, then we've seen that we can think of them doing that in a probabilistic manner, right? So you can sort of reconcile stochasticity with unitarity when you believe in causalism. That, I think, is one of the interesting things about causalism. Okay, and another difference is that the relationalism in CRQT is different from the relationalism in many worlds. In many worlds, it's about relativity to a branch of the wave function. On our approach, it's about relativity to a bubble. And as a result, for us, measurement outcomes have they are unique relative to a bubble. Okay, I think it's worth just summarizing all that we've seen in this talk because it has been a long story. In part one, we defined causation as non-commutativity. Non-commutativity of operators, but also non-commutativity of interactions. We used that definition of causal influence to define stably accessible operators, and we found that they correspond to these nice mathematical structures, and that allowed us to define events. We generalized the idea of events, and we found that events relative to a bubble always admit a natural probability distribution. We used all of these ideas to define CRQT. We saw that CRQT reproduces standard quantum predictions and also models scenarios where standard theory becomes problematic, like the Wigner's friend scenario. I mentioned a couple of other applications of it. Oh, and another thing worth mentioning about CRQT, by the way, is that there's a theorem you can prove that any experiment that you can model using the standard quantum theory, you can also write down a corresponding model in CRQT, and you'll reproduce the same predictions. So that's part of why I say it's an interpretation of quantum theory. Very good. So just a couple of thoughts to finish up on. I'm going to indulge in a little bit of speculation here. Tell you about some ideas that are kind of vague, but I think hopefully stimulating to reach research directions. So in particular, I'm going to speculate about the relationship between CRQT and quantum gravity. right? So let me mention a couple of results relating to gravity and space-time. Many of you here, I imagine, will be familiar with the Hawking-Malamud theorem, probably much more familiar than me. The Hawking-Malamud theorem tells you that in a causal general relativistic space-time, if you know the light cone structure, then you know 9/10 of the metric. Now, the light cone structure formally is like it's a continuous partial order. But you could imagine swapping that continuous partial order for a discrete partial order. And people who work on causal set theory argue that if you've got a discrete partial order, then you can recover a full metric as a kind of approximation to your discrete space-time. The trick is, so, when I talk about 9/10 of the metric, that really means that there are 10 independent functions that define the metric. The light cone structure gives you all of them except for the conformal factor. What causal set theory people argue is that you can recover that missing formal factor by counting the elements of this discrete partial order. Now we can bring in quantum causal structure. There's something called the causal atomicity theorem from quantum causal models. And it's not an entirely trivial result, but it tells you that quantum causal structures always define a discrete partial order over systems, in the case of definite causal order, at least. In this talk, we've seen how quantum causal structure can also give rise to a notion of emergent events and probabilities. So with all this stuff in mind, I now want to suggest a future direction for research into quantum gravity. So let me kind of coarse grain this picture a little bit. If we believe in causal relational quantum theory, then I think we should say that the matter distribution, right? So the thing that the stress energy tensor represents in general relativity, that should be something that gets derived from events and from the distribution of events. But if that works out, then we're talking about obtaining a matter distribution and a metric, both from the same quantum causal structure. And if we do that, we can ask about what's the relationship between the matter distribution and the metric. And we can ask, is that relationship constrained by the Einstein field equations? So, is this quantum gravity? I don't know, but I think it's an exciting possibility worth exploring. I certainly think that we're at a moment where there's a real opportunity for insights into quantum causal structure and causal relationalism to begin to inform the way that we think about unifying quantum theory and general relativity. And that, by the way, is one of the reasons why I think you should care about causal relationalism and CRQT. You might be skeptical and think, why do I need another interpretation of quantum theory? There are so many. I think CRQT is something that is kind of fresh, and it informs new ways of thinking about big outstanding problems in physics, like quantum gravity. Okay, so before closing, I'll mention some relevant literature for this talk. The notion of causation used here implicitly lies beneath various frameworks for quantum causal modeling, including these ones on the screen. For more detail on this notion of causation, you can see my paper with Augustin van Rietvelde and John Barrett. For more on causal relational quantum theory, you could see this archive paper from last year, or you could just drop me an email and ask me for my PhD thesis. And actually, I would recommend that you do that because my PhD thesis is, it's not that anything is substantively different to the paper, but I think it's presented a bit more pedagogically. Okay, there's some forthcoming stuff on causation and classical mechanics, and on the relationship between causation, stable accessibility, and decoherence. Spoiler alert, stable accessibility actually is decoherence, or rather, it's like the causalist version of decoherence. If you want literature on the relationship between CRQT and quantum reference frames, bad luck, there isn't any. But I'm very interested in the overlap between them, and I actually think that quantum reference frames could really help us to develop CRQT further and vice versa. So if you're somebody who's interested in that, that's something I'd be interested to discuss if you want to drop me an email. Okay. So I'm just about to wrap up then. So I'll just say again, thank you so much to Natalia and the organizers of this working group for having me to speak. It's been a real pleasure. someone I should have thanked earlier as well is John Barrett. So John Barrett is my was my PhD supervisor and my collaborator for pretty much all the stuff that I've talked about today. So big thank you to John for all of that. And also thank you all for listening. So I'll just leave you with one thought. I opened this talk by asking what is the role of causation in fundamental physics? And by now you know what my answer is, I guess. The central proposal of this talk is that causation is the thing out of which events in space-time emerge. So I wasn't being flippant when I made that comment at the start of this talk, right? If this is true, if causation is the thing out of events and space-time emerge out of, we can reasonably ask what could be more important, right? It seems that causation might not only play a role in fundamental physics, but it might play the very most fundamental role that there is. So I'll end there. Thanks very much.
So thank you very much, Nick, for your amazing talk. Are there any questions for the participants? So meanwhile, I will keep going on that question of mine about measurements. A continuation of the question that came to me afterwards, because you told at one moment that notion of measurement was something vague, etc. And from standard quantum mechanics would have that measurements when we use Born rule and evolution when we use Schrödinger equation.
Right.
And you told that your interpretation is just use unitaries, and even the measurements are the events that are not measurements at all are unitaries. But how can Wigner measurement be a unitary? The Wigner friend being measurement being unitary, I can get, but the Wigner one is how I can understand that.
Okay, sorry. The one bit that I missed was the very last sentence of that. Did you say that would it make sense to you that? Yeah, sorry. Can you just repeat?
Yeah, that's the Wigner friend measurement be described by a unitary. I can buy it, but the measurement of Wigner I don't see as natural. Could you say something about that?
Yeah. So forgetting about Wigner's friend for a moment.
Okay.
There's just the question of what does it mean to talk about, my measurement, say, being represented by a unitary channel. And I think the most important thing to bear in mind here is that if you are a causalist, then your understanding of the role of dynamics is different to if you are not a causalist. So if I'm not a causalist, maybe I should have a word for that. If I'm a kinematicist, then I think that the job of a unitary channel is to tell a state what to do, right? How to evolve. And when you think about unitaries in that way, it's like rules for acting on quantum states, then it's well documented that it's very problematic to think about that as representing a measurement. But if you're a causalist, then you think that unitaries have a different role. Their role is to sort of give birth to these events that emerge out of them and emerge out of them in a probabilistic manner. So the sense in which a unitary can represent a measurement on this approach is just if that unitary transformation has the right kind of causal structure to give birth to the right kind of event, right, that sort of relates statistically to other events in the right kind of way, then you can start to think about that event as kind of an outcome of a measurement, where the thing that's being measured is like an earlier event, say. Okay. Now, in terms of the Wigner's friend stuff, so yeah, I'm not sure whether that helps with whether what I've said already helps with your point about.
But I think I understood changing of perspective. I think I got somehow the idea. Yeah, I think.
Okay.
I think you answered the thing of Wigner with this. Thank you very much.
Okay, cool. Thank you.
Roughly understand, but good enough for a seminar.
Cool. Well, yeah, feel free to, you can always email me.
Please, I think Albert is waiting for us.
Okay.
You are muted,
Oh.
Albert. Albert, you are mute.
Yeah, sorry. I was just saying that a very interesting talk. I have several questions, but maybe I don't need to ask them all at once. I can ask a few and a few more afterwards. So one thing that was coming to my mind is that, I mean, the whole structure that you presented is very time reversal symmetric, right? So I guess in this context, it's very natural also thinking of the arrow of time as something that is emerging in a very similar way to what you're presenting, right?
Yeah.
Something also, well, not directly related to that, but it's that when you mentioned that that this is a probabilistic theory and that one can just, think of that, let's say maybe in the relative frequency interpretation of the probabilities and so on. But then I guess that interpretation would require that you really then have, like a system that would have many copies, many bubbles, which would be sort of more or less copies of one of these bubbles that in one of the examples that you were presenting, so that you could try to make sense of this, relative frequency interpretation of probabilities in that context. If you just have one bubble, I don't see how you could have that kind of interpretation for your notion of probability.
Well, interpretate. So, yeah, I mean, in general, right, there's a complicated foundational discussion about the meaning of probabilities and the adequacy of relative frequency interpretation. I don't have strong opinions on that debate, and I don't feel too qualified to talk about that. But what I would say about the bubble theory, and whether the relative frequency approach is problematic, I don't see any difference in this regard between the bubble theory and, say, an objective collapse theory like GRW, right? Because that's another theory in which you've got this kind of fundamental stochasticity, the way function collapses, and it collapses kind of randomly. But although the GRW theory is different to the bubble theory in a number of different ways, what it has in common is, there's only one universe, right? And so it seems to me that maybe there is a problem with the relative frequency interpretation of probabilities in bubble theory. But it would seem to me that if there is, then there's going to be exactly the same kind of problem in GRW. You're going to be able to object, but you've only got one universe. So what are these relative frequencies relative?
Right. In fact, my question was if connected to those three interpretations, in that sense, exactly the difference would be with the many world interpretation, right? So that's where there is a distinction on this issue somehow.
Right, you mean okay, because with many worlds you actually have this multiplicity of worlds, so you can,
in some sense, yeah, exactly. So that tension, I'm not sure how much it's resolved, but it certainly, I think, makes a difference, it seems to me.
I see. Well, I agree that it makes a difference. I actually think it makes it much worse for many.
That might well be. That might well be. But,
and the reason for that, in short, is that it's just not the case in general, at least on most approaches to many worlds that seem plausible to me. It's not the case in general that the relative frequencies of worlds matches the Born world frequencies. The sort of weight of worlds matches the Born world frequencies, but not the relative frequencies of worlds. So, yeah, I wouldn't want to be in many worlds there if in that kind of context, I think.
So maybe I can ask the other question is a very simple one, but so how, I mean, so you introduced in your example this reversal of the Wigner-Friends measurement, but if I understood correctly, right?
Yeah.
He was doing measurement and then he was undoing, well, not reversal, but undoing the measurement, or maybe those are not the best words. So how crucial that, I guess it's a very simple point, but I couldn't just think about it, in real time. So how crucial this is in your whole scheme. If you didn't have that undoing friend's measurement, so what's the role that that's playing here?
Yeah, I would say it's actually not playing such a crucial role. So what can I say about this?
I mean, let's put it this way. If it was not there, would you still have the same kind of structure emerging and the similar relations to the ones you had before, and there would be a difference, presumably, or?
Yeah, so here's what I think is crucial about the Wigner's friend scenario, not just for CRQT, but I guess for any kind of unitary account of it. So with the Wigner's friend scenario, let's be concrete about it. Let's say that a qubit is prepared in a superposition of computational basis states. So a qubit is prepared in a plus state. Let's say that this qubit is the thing that the friend is going to measure. The friend measures in the computational basis. So if we think about the friend's measurement as a unitary interaction, then the friend ends up entangled. It's going to be like a plus state. Okay. Now the way that I've modeled things in this picture that you see on the screen is I've undone the unitary interaction of the friend's measurement. And then after that, Wigner is just taking the qubit, which is in a plus state again, and Wigner is going to measure in the plus minus basis, say.
But in that case, I mean, the friend didn't play any role. I mean, as far as, well, you already said your finding, but it's not surprising, right? That for Wigner, if you undo that unitary, then it's not surprise.
Yeah, indeed. So another way that we could have done essentially the same measurement, right, is rather than doing this two-stage thing of first undoing the interaction and then measuring the plus minus basis on the qubit, we could have just directly measured the friend plus qubit system in an entangled basis and get the same kind of measurement statistics. And then in that case, there's no step of this undoing. So I don't know. Does that answer the question or?
I think it partly clarifies that. So maybe the only question is if you simply, so I understand your point of Wigner performing this measurement of this entangled, of this observer that corresponds to entangled. So I understand that point. But I mean, I guess the standard sort of picture of Wigner's friend and Wigner's measurement would simply not to have this undoing and not to have this non-trivial measurement of this entangled observer. So is it that it would be just a trivial thing what you get then? Or so if you apply your framework to the example where you have Wigner's friend, no undoing of Wigner's friend, and then just Wigner's measurement.
Oh, I see. Right. So just take this exact diagram on the screen and just take away that undoing interaction.
I mean, your comments were very interesting in clarifying why you had that there. But if we take, the undoing out and you just, consider your framework, so what's the conclusion we reach then?
I see. Okay. So okay. So if we take out, let's just talk about the circuit for a second first. So if we just take out the undoing measurement, the circuit no longer represents anything particularly exotic, right? The circuit just represents a kind of situation where, we don't have to talk about a friend inside of a lab or whatever. We can just say Wigner and the friend are standing side by side. Friend measures particle, then Wigner measures particle, and so on. So it's not a particularly exotic kind of experiment. We could write down that circuit, and then we could pick a bubble that includes state preparation and the friend's measurement and Wigner, who's not really Wigner anymore, his measurement as well. And we would just find that we get the same kind of statistical predictions that we would expect just playing the orthodox interpretation of quantum theory.
Okay. So I see. So this was really trying to look at probing the non-trivial aspects of this situation. As you were saying, maybe another way of thinking about it was if Wigner was trying to measure this operator corresponding to the entanglement between.
Yeah. So the reason, one of the reasons I talked about the Wigner's friend scenario was I wanted to illustrate the kind of relationalism in the theory. And the reason we saw the relationalism come up was there was this point about the friend's sort of outcome projectors not being stable relative to Wigner. And that meant that like when you include Wigner in the bubble, you're not really yeah, it's like the friend doesn't perform a measurement. Whereas in that like non-exotic scenario that we're talking about now, where you remove that transformation from the circuit, you wouldn't have anything like that happening. All of the different agents would be sort of completely stable relative to each other.
Okay, thank you. Thank you very much. Very interesting. I'll let the others also ask their question.
Yeah. Fabio, you wish to make a question, I guess.
Yes. Thank you for also staying so long. It's been a very nice talk, very interesting. Maybe first a comment, maybe just a terminology. I think the way you use the word causal and fundamental causation and so on is a bit diverging for a more traditional use in a few ways. Maybe we'll spend too much because this terminology, but as Albert pointed, usually causation is strongly associated with the one-directional concepts. I would say what you present very strongly looks like a process ontology model where the real thing is the process, and then you use causal relations to describe properties within the process. So this is just a comment about terminology, not too important. My question would be, so you try to say that these processes, these unitaries, these circuits are the real thing. So supposedly there is only one true circuits in the universe, and then you isolate the bits and pieces of that. How does that square with some situations with where the circuit itself could have some quantum aspects or undeterminate aspects? So since we are on this Wigner friend and related to Rura's question, so imagine that the second, just to make an example, the undoing part of the circuit is conditional unitaries. You add another system and you condition and you make it conditional. So you say that I have yet another system that can be 0 or 1. And then if it's 0, I do the undoing. If the system is 1, I don't do the undoing. So in that case, I could say, well, this is the particular case that I see when I choose the particular state of the other system. The more fundamental and true one will be this extended circuit. And then your conclusion and your analysis will depend on that. Now, my question is, how does one stop? So arguably, any little circuit that you extract will never be the real, a part of the real thing. It will always be conditional on having fixed some state somewhere to decide what process we're looking at. So how do you see this if you try to say that these are the fundamental things?
Yeah, no, I think it's a great point. It's a great question. Whenever we're drawing like any circuit that could ever fit onto a PowerPoint slide is not going to be a circuit that includes everything. So whenever whenever anyone actually draws a circuit, it's never the circuit, right, that describes everything happening in the universe. I would say that CRQT, as it currently stands, if it's to be intended as like an actual proposal for the correct interpretation of physics, I think it would have to say, well, look, even if nobody's ever written it down or nobody ever can write it down, there is one fundamental circuit representing all of reality, and we're all living in that circuit, and we're all made out of the events that emerge from it. But if you do that, then there is this important question of, well, given that no one's ever going to write down that whole big circuit, how do these smaller circuits that we write down, these non-fundamental circuits, how do they relate to the bigger circuit? How reliably can we use these smaller kind of effective circuits to reason about the fundamental one? And I think this is a genuinely interesting and non-trivial question. And I'd like to be able to say more about it, but I can't say too much more about it at this stage. So yeah, great question.
So Albert, I think you wanted to keep asking.
Yeah, I mean, if others have questions, but this is really a follow-up just to this question and answer. So in the sense that I also saw a lot of connection with causal set theory, that this could kind of, and you emphasize that aspect as well. But connecting to Fabio's question, I mean, wouldn't I think of in typical causal sets, I would think that I have different possible causal sets, that presumably our world, our universe is really a superposition, a quantum superposition of many of those causal sets. So wouldn't that correspond to having a quantum superposition in your language of many different circuits? And
Well,
that maybe connects to Fabio's question.
yeah, I think it does. Okay, so yes. So how do we? Does the idea of superpositions of circuits play a role in this interpretation, and how can we understand them? So the first thing to say is I want to resist the idea that there's such a thing as a superposition of circuits. I think you can make sense of that idea in some way, but strictly speaking, I think that's kind of the wrong terminology. And the reason I say that is just because, remember, on this approach at least, events are things that emerge from the causal structure of a circuit, and then states are tools that we use for computing the conditional probabilities of events, right? So quantum states are things that come out of a circuit and describe the events that come out of a circuit. Therefore, a circuit itself isn't really the sort of thing that has a quantum state. There is no quantum state of the circuit. And if there's no quantum state of the circuit, then strictly speaking, there's no such thing as a superposition of circuits. Now, that doesn't mean that you can't make sense of a sort of analogous idea. You can talk about these kind of like coherent control interactions. Fabio mentioned earlier this idea of like coherent controlling, whether you undo the measurement in the friend scenario. And in that case, you'll see these coherent control interactions in the bigger circuit, and you'll be able to understand this idea of like a coherent control of circuits by actually looking into the causal structure of that bigger circuit. Right. So by delving into the causal structure, kind of at the fine-grained level, you'll be able to see that, oh, in this kind of part of the process, we've got like this sort of effective causal structure in this region of the circuit, whereas in this other part of the process, we've got this other effective causal structure. So it's like, yeah.
For that example, I would agree completely with you.
Mm.
So that's why maybe my question is not 100%, but it's really the connection with causal sets that and how to apply this framework to causal set theory. Because
Right.
in causal sets, the causal structure, different causal sets correspond to different causal structures. So it's a bit like the difference between, the tension between quantum mechanics, so quantum field theory and general relativity, where space-time is the arena, and the causal structure is given, is set, is there. And there, yes, I mean, all these things, a single circuit, I mean, I can see how all that would work. But the moment that also is quantum mechanical, the causal structure, and you don't have a unique, well-defined causal underlying something leading to that causal relation, so to speak, as in causal sets, where for each causal set, yes, you have a causal relation, a set of causal relations, or causal partial order that corresponds to, but then, you can have a superposition or different causal sets. And so I'm just wondering how that would merge with or how you would fit this framework.
Yeah. So when I was, at the end of the talk, I said these very sort of
yes, that's
speculative things about
yes,
about quantum gravity. So this approach to quantum gravity, or this even an approach is probably generous at this stage, but this kind of idea for an approach to quantum gravity on the screen here, it's certainly related to and partly inspired by causal set theory, but it's also importantly different from causal set theory in certain respects, I think. So the idea that we're kind of taking here from causal set theory is the idea that there's some kind of causal structure that's described by a partial order, and then space-time is just something that emerges from that causal structure. But the thing is, from my point of view, or from a causalist point of view, it's kind of a bit weird that in causal set theory, these discrete partial orders are called causal sets, right? Because they're really, as you say, they're things that you can put in superposition. They're kinematical notions, right? I guess the reason they're called causal sets is because they end up having this connection to the light cone structure, and people often associate the light cone structure with causality. But really, from my point of view, causation, properly speaking, is a dynamical notion. So if I just write down a partial order, there's nothing essentially causal about that, even if it is a partial order. So on both this approach to quantum gravity and in causal set theory, you're trying to argue that a space-time emerges from a partial order. But on this approach, the significance of that partial order is different and the origin is different. So you start with a unitary circuit, you derive the partial order from the causal structure, and then that's how you hope to argue that space-time emerges. And because of the fact that the discrete partial order on this approach is coming out of the circuit, and as I said, a circuit is something that, properly speaking, it doesn't get put into superposition. On this approach, you're not, strictly speaking, going to have any such thing as a superposition of causal structures. And so one of the things that I think is potentially interesting about this idea for approaching quantum gravity is that I see it as a way of potentially avoiding this idea of a superposition of space-times. Now, we're still obviously going to have to make sense in any quantum theory of gravity of like this relationship between matter and space-time structure that we see in general relativity. But I expect that we can do that by appealing to this idea, this fine-grained causal structure that I was mentioning earlier, where like you delve inside the process and you see that like within this part of the process, you see this effective causal structure. And in another part of the process, you see another effective causal structure.
I see. So your idea is more that you have this given underlying sort of structure, and then you expect to have these sort of notions of causation and so on emerging there. I can see that, but somehow as opposed to causal set theory, the really underlying structure of things that are connected somehow by unitary, different nodes in some sense are there.
Yeah.
Are unique in some sense. There is only one. And
yeah, maybe another way of thinking about the difference between these approaches is that in causal set theory, like you write down this causal set, right? And you argue by Hawking-Malamin type theorems that space-time emerges from it, but you want to do quantum gravity, right? And there's nothing quantum about this so far. Like you have to put in the quantumness somehow. And roughly speaking, as I understand it, at least, the way that you insert the quantumness in causal set theory is essentially by saying, okay, well, these causal sets can kind of have a quantum state, or they can be put in superposition, or we can define path integrals with them, right? So you're treating the causal set as a kinematical object, which from my point of view on causation wouldn't make sense. So on this other approach to quantum causation that I'm proposing on this other approach to quantum gravity that I'm proposing on the screen here, it's different because you start with a unitary circuit. So you're starting with the quantumness. The quantumness is there from the very beginning. It's a unitary circuit you're beginning with. The partial order or the causal set that you're deriving is just a description of the causal structure of that circuit, which means the quantumness was already there before the time you got to the causal set. And so you don't end up in this position that you end up in with causal set theory, where you think, okay, I need to add in quantumness and let me put things into superposition. It was already there.
Yeah, I guess that, I mean, I see it's very good that you emphasize these important differences. I think that probably one of the motivations in causal set, that approach is really this approach to quantum gravity, believing that you should have some sort of background independent structure. Whereas in your case, it seems as if there is, not in the sense of the quantum mechanical maybe relations in dynamics, but in terms of this underlying structure that corresponds to your circuit, which then has different elements, that's a given background. So I think that that's an important, it seems to me, aspect that distinguishes.
So what I would say about that is, so with a circuit, right, you can start with a circuit, but then you could represent that same circuit in a very kind of Heisenberg picture way, where like you essentially just like you replace the wires with just like labels of operator algebras, and you've got like these arrows between the operator algebras. Like you can think of a circuit as being like a DAG of operator algebras essentially. And I don't know, would you call that a background? Would that constitute a fixed background for you?
Well, I guess I'm not.
Yeah.
Yeah, I'm not. I'm not. I'm not. My knowledge about the operator algebras and so on is not good enough to see how much flexibility. I see that there is that not everything is fixed and that you have a lot of freedom, but I'm not sure that you would still have a certain level of background structure.
I think that the background structure emerges from the relations between these blocks. This. So this is the relations. I'm seeing here relationalism also very fundamental in this theory. Not only the causality, because without the relation between these diagrams, between these processes, it is background dependent. When you add relationalism, it is independent.
Right. Yeah, I don't know. I guess I'd always kind of assumed that if you just have this DAG of operator algebras, that would mean it's a background independent model. But I guess what I'm realizing now is I need to think harder about exactly what background independent means, because now that I think about it, it seems kind of elusive.
Yeah, I mean, if you think of a given space-time in quantum field theory, it could be even simpler, but on a given fixed background space-time, I don't know, there you can think in terms of operator algebras and so on and so forth for the quantum fields evolving in that fixed background space-time that in some sense gives some, well, causal structure, at least in the sense of partial order, if you wish, or that would just emerge out of, or you could have that on top of this given background space-time structure. So in that sense, yeah. Anyway, I don't want to. It's been very long and very interesting discussion,
but yeah, thank you though. That's very interesting.
Okay, so thank you all for the great questions, and thank you, Nick, for your amazing seminar. I think I should stop recording now. Thank you for those who watched the video.